alternating current and voltages. You see, an alternating current or voltage is one that varies periodically in such a way as to reverse its direction periodically as well. You see, the equation of alternating current and voltages is given as shown here. This is the equation for alternating current, and this is the equation for alternating voltage, where I here means, or I subscript T means the current at any instance of time, and Im here means maximum current, F here means frequency in Hertz, and T means time, while V subscript T means voltage at any instance of time, and Vm here means maximum voltage, F means frequency, and T means time. Next, let's look at the root mean square value of current or voltage. If you say root mean square current, what does it mean? The root mean square value of an alternating current is that steady current which develops the same quantity of heat in the same time through the same circuit. You see, the root mean square current is the DC equivalent of an alternating current. If you have an alternating current, what is the quantity of DC that would do the same as that alternating current? That is what we call the root mean square current. And the root mean square voltage still means the same. It means the root mean square voltage is the DC voltage that will do exactly the same as the alternating voltage. So that's that about that. We have that the root mean square value of current is given as maximum current over root 2. Some have it to be like this because this can be 1 over root 2 times maximum current. And you see, if you evaluate 1 over root 2, you're going to have 0.7071 Im. So this is it. It can be like this. And for root mean square voltage, it can also be 0.7071 maximum voltage, or maximum voltage over root 2. Example 1. An alternating voltage is given by the equation V subscript C is equal to 282.3 sine 314 T. Find A, the root mean square voltage, B, the frequency, and C, the instantaneous value of voltage at T equal to 4 milliseconds. Let's solve this question now. Firstly, we are given that V at any time T is equal to 282.3 sine 314 T. And we know that our equation for voltage or instantaneous voltage is given as maximum voltage sine 2 pi ft. If we compare these two equations, we have the maximum voltage is given as 282.3 volts. Hence, we can now look for the root mean square value of voltage. Vrms now is Vm over root 2. And that will be 282.3 over root 2. So 282.3 divided by root 2. And this is 199.62 volts. The next we want to look for is the frequency. You can compare this after whatever is after the sign compared to whatever is after the sign here. That will be 2 pi ft is equal to 314 T. T eliminates T. Dividing here by 2 pi and dividing here by 2 pi. Where the frequency is equal to 314 divided by 2 pi. That's approximately 50 Hz. Now, lastly, we want to get the instantaneous value of voltage. That would be Vt at t equal to 4 milliseconds, sorry. So we have that t is 4 milliseconds. That is 4 times 10 raised to the power minus 3 seconds. So let's go back to our equation for instantaneous voltage. That's 282.3 sine 314 now times 4 times 10 raised to the power minus 3 seconds. That's what we have. So let's evaluate this. So we have 282.3 sine 314 times 4 times 10 raised to the power minus 3. So this is 268.43 volts. Now, mind you, if you evaluate with me, you may not get this answer. That's because your calculator may not be in radian. To evaluate this, please take note that our angle is in radian, and because of that, you must convert your calculator to radian before you evaluate. Or, if you multiply these two, whatever it gives to you, convert it to degree first before you evaluate. So that's for this question. Example 2, calculate the DC equivalent of a 120 volt alternating voltage. So here we have that our alternating voltage is 120 volts. Then what we have to get is the VRMS. That is the DC equivalent. So VRMS is just going to be 120 over root 2. That's 84.85 volts. That's the DC equivalent. Purely inductive AC circuits. A purely inductive AC circuit is an AC circuit that contains only an inductor. This is an example of an inductive AC circuit. The circuit contains only an inductor, and so this is the AC supply. You see, the opposition the inductors offer to the flow of alternating current is known as inductive reactance, and it is measured in ohms. So you see, we use the word reactance when a capacitor or an inductor is involved, while we use the word resistance when it's a resistor. All of these things are opposition to current flow. So the opposition to current flow due to a capacitor or due to an inductor is called reactance. So when we say capacitive reactance, it's because it's a capacitor. When we say an inductive reactance, it's because it's an inductor. So here we're looking at inductive reactance. The L here is the inductance of the inductor. It's measured in Henry. And then the F is frequency. XL means inductive reactance. Now, one thing I want you to take note is that in a purely inductive AC circuit, the voltage leads the current, or the current comes behind the voltage or lags the voltage. So voltage is ahead, and well, for this we are using the voltage as a reference. So the first angle here is 90 degrees actually. So the voltage leads the current by 90 degrees. And so this is an illustration of what we are trying to say. If you look at this now, you see that why the current is starting 0, because this is the current actually, this is the current. This is the current. Why the second, here is the voltage. So why the current is starting at 0, the voltage has already started earlier. So the voltage here is leading the current. The current is just starting while the voltage has started long before the current started. So that's the illustration of what we are trying to say. Let's take this first question. Calculate the reactance of a coil of inductance 0.32 Henry when it's connected to a 50 Hz supply. So we are given here the inductance of the inductor 0.32 Henry, and we are given the frequency 50 Hz. So the inductive reactance is 2 pi FL, which will be 2 pi times 0.32 times 50 times 0.32. So this is 100.5 ohm. Example 2, a coil has a reactance of 124 ohms in a circuit with a supply of frequency of 5 kHz. Determine the inductance of the coil. Here, to solve that question, we are given the inductive reactance 124 ohm, and then we are given the frequency 5 kHz, which is 5,000 Hz. That is just times 1,000. Okay, so we have to get the inductance of the coil. That is, we are looking for L value of the coil. We know that XL is equal to 2 pi FL. Then L itself will be XL over 2 pi F. Our XL is 124 divided by 2 pi times 5,000. This will give us 3.95 times 10 raised to the power minus 3 Henry. Purely capacitive AC circuits. An AC circuit that contains only a capacitor is called capacitive AC circuits. Now, the opposition the capacitor produces to current flow is known as the capacitive reactance. It is measured in ohms and is given as 1 over 2 pi Fc, where C is the capacitance of the capacitor and F is frequency. And now, in a purely capacitive AC circuit, it's important to note that the voltage is behind the current, or the voltage lags the current by minus 90 degree or by 90 degree. So we take the first angle to be negative 90. The graph of current and voltage is shown below. As we look at here now, we see that while the voltage is starting from 0, the current has already started. So current is ahead of the voltage, or voltage lags the current. Now let's look at this question. Determine the capacitive reactance of a capacitor of 10 microfarad. So we are given the capacitance of the capacitor here. 10 microfarad, which is 10 times 10 raised to the power minus 6 farad. And then the frequency, 50 Hz. Calculate the voltage, we have to determine, the capacitive reactance. So that's the first thing we have to get here, capacitive reactance, and that's 1 over 2 pi Fc. So that will be 1 over 2 pi times our frequency 50, then times the capacitance, which is 10 times 10 raised to the power minus 6. So let's evaluate this now. So this will give us 318.34 ohms. Then the next one we have to get is the voltage. Now, Ohm's law applies here as well. V is equal to, but not IR now, but IXC. If it's an inductor, it will be V is equal to IXL. So this will be current. The current is given in the question to be 20 ampere, then times 318.34. So that will be 6,366.8 volts. Purely resistive AC circuits. A purely resistive AC circuit is an AC circuit that contains only a resistor. And we know that the opposition to the flow of current or alternating current in this circuit is due to the resistor and is measured in ohms. Now, in a purely resistive AC circuit, the current and voltage are in phase. They tango. Let me use the word tango. But it means that they move alike. When voltage gets to the maximum, current is at the maximum. When voltage is zero, current is zero. They move alongside together. So they are said to be in phase. RL series AC circuits. Now, this is an AC circuit that contains a resistor and an inductor. Now, the opposition to flow of current in this circuit is known as impedance. You can't say it is reactance here. If you're saying reactance, you're saying it's just due to the inductor. And you're not saying it is resistance. If you say that, you're saying it's due to the resistor. But the combined opposition to flow of current due to the resistor and inductor is called impedance. You see, the impedance, Z, is impedance, is given as square of the resistance plus square of the inductive reactance, all into square roots. Is the formula for the impedance. Now, the voltage supply in this circuit is given as I times the impedance. This is the voltage supply in this RS series AC circuit. And then the phase angle here is given as phi, phase angle. Is given as tan inverse of XL over R, or phi also is given as tan inverse of voltage in the inductor over voltage in the resistor. And it's important to note that the voltage supply V is equal to voltage in the inductor square plus voltage in the resistor square, all into square roots. So that's that about this. I want you to take note again that the phase angle is usually greater than 0, but less than 90, or you say pi over 2. Now, what is the reason for this? Now, remember that we have a resistor and we have an inductor. If it's only a resistor, phase angle is 0 degree. If it's only an inductor, the phase angle is 90 degree. When you combine these two, the phase angle will fall between 0 and 90. And it will always be positive. So that's what. It's always positive. Let's put that. It is always positive. Example 4. In a series RL circuit, the PD across the resistor R is 12 volts and the PD across the inductor L is 5 volts. Find the supply voltage and the phase angle between the current and voltage. Well, here we are given that the voltage across the resistor is 12 volts and the voltage across the inductor is 5 volts. Hence, the voltage supply will be voltage in the resistor square plus voltage in the inductor square, all into square root. And that will give us 12 square plus 5 square, all into square root. This is actually 13 volts. Now, the next one is number 2, the phase angle. The phase angle is given as tan inverse of XL over R. And that is tan inverse of our XL, sorry, not SL, because we're not giving S, it's VL over VR. Our VL here is 5 divided by VR, 12. And this is 22.62 degrees. Example 5. A coil of inductance 318.3 millihenry is connected in series with 200 ohm resistor and to a 240 volt 50 S supply. Calculate A, the inductive reactance of the coil. B, the impedance of the circuit. C, the current in the circuit. D, the PD across the components. And then E, the circuit phase angle. Okay, let's solve this question now. First of all, let's bring out what we are given. We are given the inductance, which is 318.3 millihenry. And then we are given the resistance here, 200 ohms. Again, we are given the voltage supply, V, 240 volts. And again, we are given the frequency, 50 Hz. Okay, so for the first one, inductive reactance, that's XL. That's given by 2 pi FL. So 2 pi times the frequency, 50, times the L, 318.3 times 10 raised to power minus 3. Because this is millihenry, you convert to Henry. That's 10 raised to power minus 3. So this will give us 100 ohm approximately. Now, the second one here is the impedance of the circuit. Since we have our XL, now we have our R. Impedance Z is equal to R squared plus SL squared all into square root. And that will be 200 because our R is 200. 200 squared plus 100 squared all into square root. If we do this, we are going to have 223.6 ohms. That's our impedance. Now C, the current in the circuit. Remember that voltage supply is equal to current times impedance. So our current can be the voltage supply over impedance. The voltage supply is 240. Our impedance is 223.6. This will give us 1.073 ampere. Now D, the PD across the components. Voltage across the resistor is going to be IR, which is I 1.073 times R 200. So this is going to be 214.6 ohm. Then voltage across the inductor is simply going to be IXL, which is 1.073 times 100, and this will be 107.3 volts. Volts. This is volts actually. And the last but not the least is the phase angle, phi, tan inverse of XL over R. So this will be tan inverse. Our SL is 100, our R is 200, and so the phase angle is going to be 26.57 degrees.